So I'm going to talk about the SYZ-conjecture. A lot of the things I say will be for hypersurfaces and toric fundaments. And then whenever I talk about my own results, it's based on a few collaborations with Mattias Jonsson, Enrica, Mazzon, McCleerey, and Rolf Andreasson, and and then I was also asked to give some kind of general background to the field, which I think, I'm not sure if that's a wise decision, because I somehow answered this pretty late, but I will do my best to talk about this, say something about the background, and in particular I'll talk about sort of a recent breakthrough when it comes to this differential geometric perspective on the SYZ-conjecture, which is due to Yang Li. So I'll give some kind of background to that before I will get into things that are closer to the stuff I have been working on in the second lecture. So this then, well, it's about the SYZ-conjecture. So it's the basic idea of that is to view your Calabi-Yau manifolds as fibers over some discrete space, and then you would get the connection to mirror symmetry, that you would get the mirror by somehow dualizing this discrete space. So that's what I'm trying to convey in this image here. So we have a Calabi-Yau manifold, and it's fibers, tori over some kind of discrete at the bottom there.
Jakob Hultgren, will you make the slides available after the talk? People don't need to take notes. The slides will be available.
Yeah. And there will be like I'll make a lot. There will be a few connections with Siebert's talk, but I think I'm going to approach things from a different angle. So usually I will start with instead of starting with discrete data and get Calabi-Yaus, I will start with Calabi-Yaus and try to extract discrete data and then talk about these vibrations. So I'm going to begin with an example then of the dwarf families. These are just hyperfamilies of hypersurfaces in projective space. So I'm gonna, my T here is just a positive parameter, or a non-zero parameter, and so of course then if I do this for so my ambient space here is my hypersurface has dimension d+1. So if I do this for d equals 2, then I get this family of elliptic curves. So essentially x, y, c minus t x cubed plus y2 plus c cubed. So which is of course then a family of elliptic curves generating into this union of the coordinate hyperplanes in C2. So okay, so what do I see when I see this thing? So my background is in complex differential geometry. So the first thing I see here is that this is a family of Calabi-Yau manifolds. So the canonical bundle is trivial, which means then by a theorem by Yau that these xt they admit Ricci-flat Keller metrics. So I can think about this as a family of Keller manifolds, xt together with these Calabi-Yau metrics. And these Calabi-Yau metrics, they are quite transcendental in the sense that they're quite different from the Rubini-Studni metric of this embedding, for example. So one thing that's going to happen is that as t tends to 0, these Calabi-Yau metrics, they're going to give most of the mass in these Calabi-Yau metrics are going to be given these sort of intersections, the deepest intersections of the central fiber. somehow those points converge there. I'm going to move to a slightly more general setting, or maybe I'll just, yeah. So we're going to look at hypersurfaces in toric Fano manifolds. So I'm going to start with Y, a toric Fano manifold, and its dimension is P plus 1. Then this is my P plus 1 dimensional projective space. I get the character lattice M with dual N. Then we have a moment polytope in MR, just this corresponding vector space, and we got a dual vector space as well. So I'm going to start with this data and one more piece of data. So it's a weight function defined on the lattice points of my polytope minus the origin, and it takes values in positive values, integer values, and it can also take the value plus infinity. And I also want it to be convex. Then this data gives me a family of hypersurfaces in the toric Fano manifold, and anticanonical hypersurfaces. And they, you see here how my H somehow encodes some kind of generation of these. So if you compare this to the previous slide, where I had projective space, then the moment polytope of P2, the way I usually normalize it, looks like this, where I have the origin in the middle. We have this unique interior lattice point, and then there are a number of lattice points on the boundary as well. And so the dwarf family I talked about on the previous slide, you get it by putting one here, and one here, and then plus infinity on the rest of these. That would mean that these three boundaries, these three vertices here correspond to these three monomials over here. And then we have these torus invariant section F0. Is that all right? Yeah, no problem. So we have what we saw before was something generated to these microplanes in P2. In general, here we get something then that generates to the toric boundary. So we have a family of Calabi-Yau generating to the toric boundary. Now, the SYZ-conjecture then, where it says that this one way to formulate it is that these four small t, when we're concerned with this family, then xt is expected to admit a special Lagrangian torus vibration over a base, which would be the.
Somewhere you made this Calabi-Yau. Did you make an assumption with Calabi-Yau?
So they will always, well, so I'm always looking at this family right here. And so what I have here is this is an anti-canonical device. for a fixed T, I get an anti-canonical device. And the Enrica. And right, so I'll say something about what this means here. So we're expecting to find a torus vibration, but it should also be special Lagrangian. So I will introduce a little bit of terminology to say what that is. So the fact that these are xt are Calabi-Yau, that means we have these triple. We have complex manifold, and we have a calorimetric, and we have a holomorphic volume form. And they are compatible in the sense that I take the calorimetric to the top power, I get like the same as, but I get my holomorphic top form.
And you wrote as V, so you really expect a sphere.
I do, yeah. I expect to see.
So this involves other conjectures.
Probably many conjectures, yeah.
So it's not only, it was say plus several other conjectures.
Probably, yeah. So, yes. When I'm in this setting here, the natural candidate will be homomorphic to ST, but that's not the question. Okay, so in such a Calabi-Yau manifold, we have a submanifold is Lagrangian if its dimension equals D. So its real dimension is D. So we have complex dimension is Calabi-Yau is D, and a Lagrangian have real dimension D, and also the Kähler form or the symplectic form vanishes. Restricted to. So these let me also write down what it means to be special Lagrangian. It's if the imaginary part of the holomorphic volume form also vanishes. So these Lagrangians, let's say if we fix any complex submanifold of my Calabi-Yau manifold, then these the symplectic form, they will restrict to another symplectic form. So these Lagrangians, they're somehow orthogonal to complex submanifolds, so they're the opposite of having a complex submanifold. Then these are then the conditions for being a special Lagrangian. So the most simple example is yes, look at the quotient of the complex plane, and you just map it down to a circle. Then you have a special Lagrangian torus vibration. I will talk about, but there is another way to sort of cook up examples of these, which is related to real Monge-Ampère equation, which I will mention here as well. So if I have or maybe I will.
Recording in progress.
Before I say that, I will also introduce something which is well new then, since Yang Li's work, which is the a weak version of this metric SYZ-conjecture, where we somehow focus on these Calabi-Yau metrics, and we ask for the special Lagrangian torus vibration to we ask to find a special Lagrangian torus vibration almost everywhere, but not almost everywhere as a mathematician would interpret it, but really sort of on almost all the volume of our manifold. So the weak metric SYZ-conjecture for these families says that for any delta larger than 0, for small enough t, there is a special Lagrangian torus formation on a subset of the Calabi-Yau, which is of sort of arbitrarily large relative Calabi-Yau volume. So when I write absolute value of these sets, then I mean essentially computing the volume with respect to the holomorphic volume or the volume form associated to this Calabi-Yau.
What's the difference between his, well, this is also asymptotic. What is the asymptotic?
The Lagrangians are not
Actually,
special, they are asymptotic.
I see here they're really special. That's why this is a big deal.
What happens with what you said that as you degenerate, all the volume is concentrated on the singular part. So this means that also most of the
It will be concentrated near the deepest intersections, but this area is somehow the least singular in the asymptotic picture we get here.
okay.
So they would correspond to these deepest intersections. They correspond to kind of large annuli in your Calabi-Yau manifold. And the singular fibers in this vibration, they would be away from those. They will not be close to the deepest intersections. So I had so there was a question here about how to interpret this. So for each t here, we have a Calabi-Yau manifold, xt, and this here says then that we have some singular central fiber, and then this theorem here says that if out here I probably have a special Lagrangian torus formation of a very small set, but as I get closer and closer to the central fiber, sort of the relative volume of this set is bigger and bigger. And what is happening here is that if I sort of in the SYZ-conjecture you expect to get the torus formation is not expected to be smooth. It's very easy to see that it cannot be smooth. So somehow we are staying away at a positive distance away from these singular loci, the singular fibers.
So in the kind of rigid picture, you would rigid analytic picture, these fibrations are away from the kind of double locus of the central fiber.
Possibly, I'm not. I might be able to answer your question in sort of in the non-Archimedean framework.
Yeah. So you have these double points, right?
Yeah.
At the where your fibers cross. And you have these discs that would intersect the locus, and at the double locus you need a kind of order 2 thing. So they're right.
I might need some more context to answer the question.
I'm asking what the flavor of the UT is, so to speak.
Yeah.
So
maybe I can get back to that. I will be quite explicit later on.
But geometrically, you would think that the UT, when you maybe an easier way to ask the question: what is the limit of UT when you go to t equals 0?
So what was the limit of the image of UT?
No, it doesn't make sense.
On the base?
No, you have a family, right? So you kind of
Yeah.
you can.
You mean the limit
Do they stay away from the double locus?
You want to say the limit
In the metric you see.
in Fubinius to the metric.
Excuse me?
In
In
the
Fubinius to the metric.
Yes.
It is the maximal intersection of the.
yes.
They
it is
all
the-
converge to the maximum.
Yeah.
Okay.
If you look for some, you get the.
So it's away from the.
So all of these regions,
Oh, that's
although
right, yes.
they are big in the Calabi-Yau
I remember
sense,
that, yes.
they're all
Yeah,
concentrating near
yeah,
these
yeah,
deepest intersections. That's a very good question.
That UT is disjoint, like as many components.
I will get back to that, but in general it seems so, but not always. Okay. So there are, yes, I will.
In these values, why SYZ vibration connects to the submaximal intersection.
Yes, it's not disjoint. I mean, there are also the very, very.
No, but the
small
way of
things.
defining UT here is disjoint, but they are not considering the whole SYZ vibration.
If you just look the way I said it, they will concentrate. UT will concentrate near the deepest intersections. Of course, they are not. I mean, these
And for
are
the passage, you'll also have, but it's just very small area.
exactly, yes. There will be a kind of small area apart with connected. But this is only known for some examples, not all examples. Where there are cases when this is known, but it's not known that UT is actually connected. That sort of comes down to a regularity statement for real Monge-Ampère equation, because that's going to dictate what our UT will be.
So you're never identifying the fibers using symplectic parallel transport, right? Are you identifying fibers?
Yeah,
Like when you say, for example, they all converge to.
yeah.
In what sense do you say that?
So I didn't want to say it, but somehow that's where most of the things happen. Yeah.
I said something a bit wrong, but I don't want to confuse people. So I was referring to the UT in the paper in which Yang Li was able to prove the conjecture. And there it is disjoint, but you can conjecture that UT is larger and then the limit
So
is larger than the maximal intersection between maximal and submaximal at least.
But this is where you have this kind of finitely number. You would like to impose some conditions on the polytope to be able to connect.
Yes, there will be some conditions, and in fact, like after Yang Li's paper about the Fermat family, then there is this. But we know by regularity of the Monge-Ampère equation that you can actually extend this UT to make them connected. You can actually know more or less what they do. Okay, so let's see, where am I here? Yes, so, right, so I wanted to give some more examples of how to produce the special Lagrangian torus vibrations. And then what I will do is I will work somehow backwards, and I will give sort of local examples of special Lagrangian torus vibrations. So then I will fix a U that's a convex subset of RD, and I will fix a psi, which is a function from U to R, which is convex and twice differentiable. And I also want this to satisfy the determinant of the second derivative. I take this Hessian matrix and I take its determinant, and this should be constant. If I have such a thing, then the log map from RD to then I also introduce the corresponding analyte, which are parts of C star to the power of D, and they are such that if I take the log map, then their image is U. And here the log map is just coordinate-wise logarithm. So log map maps point down to logarithm of the absolute value of this. So if I have this data, then
say you open.
U is open, yes.
AU also.
AU is also. Then
you're going to say take the full image.
sorry.
Is AU always the full inverse image? Or
Yep.
AU is
I always take the full image. Then this map, then AU natural Calabi-Yau structure. And I'm not going to write down exactly what it is. I'm just going to say it works. So AU, we get the holomorphic volume form from here, and this solution or this psi here, it defines a Keller metric on AU, a torus invariant Keller metric AU, and these are and then this logarithm is special Lagrangian torus vibration.
So Keller metric is kind of the biggest DDC of
It's yes, it's sort of, if you just extend, you can lift this back to the annulus, and then you take these. So in this case, these conditions for the submanifold via special Lagrangian, they follow somehow automatically. And the sort of somehow key technical part is that we need, this part is needed for this for this to actually be a Calabi-Yau structure. So the fact that you have this real Monge-Ampère equation here means that the holomorphic volume form I get from here and the Keller form I get from psi are compatible in the sense I mentioned. This compatibility condition. So this is a way to produce these local special Lagrangian torus fibrations. And the idea to get these weak metric SYZ-conjecture is to somehow produce a bunch of those and glue them together. To do that, you need to understand like what local pieces am I going to use, and that to do that you look at these sort of tropical objects associated to these families of Calabi-Yau. So first of all, there is this. If you remember, I had this family F0 plus some e to the power of HM FM.
One question: what is the relation between this glue with the original metric that you would be?
You mean the original Calabi-Yau metric?
Yeah.
On these? They are very, very close to each other. And that's somehow the key part in this whole story, to show that they're very close to each other. So then what you have then is some kind of prelude version of an SYZ vibration. But it's not really consistent where it overlaps.
Okay.
But then you use perturbation results essentially that show that you can actually deform this to a proper SYZ vibration, at least on a large subset.
Sorry, I didn't get it. What is close to what? So you.
Yes. So the here I produce these local Calabi-Yau structures. They have Keller metrics, and in the end they will be very close to the actual Calabi-Yau metrics on the Calabi-Yau manifold.
On your particular Calabi-Yau manifold.
Yes, xt for xt.
Okay.
Sorry, on this slide, what was AV? Can you say it again?
AU.
Oh, AU.
I fix a convex subset of RD.
Yeah.
Then I get a corresponding subset in the annulus, which is just the
Oh,
inverse image under the log map.
Oh, I see.
I wrote it in a somewhat backward manner.
But this is expected, it's not just for particular color, this is expected to be in general.
Yeah, but in
Calabi-Yau.
Right.
Yes. So there's a map. So this log map I talked about before, it can be made like a little bit more coordinate invariant on toric manifolds. You can actually define get a log map which goes from the complex torus in my toric Fano manifold down to NR. This is so my complex torus here. It's n tensor product C star. Then if I say I have an element of this form in here, I can map this to log C times n in here. It's just a coordinate invariant way to say that we have a complex torus in our toric Fano, and we want to sort of use the mapping to NR using the logarithm coordinate. We can also scale it. T. So I'm gonna write 1 over T. And then we can look at the images of xt under this map. So the image I have here comes from the work family, where we have h takes value 1, 1, and 1 here, and plus infinity elsewhere. And this one looks just like xyc plus g x cubed plus y cubed plus c cubed. So for this expression, essentially, so this is very, very concrete, like for this expression to be 0, at least 2 of these monomials we have here have to be of comparable size. And being of comparable size, that sort of translates into something that you will map to a certain region under the log map. So what's going to happen is that these Calabi-Yau manifolds, as T becomes small, the image will somehow look like this in NR. So a thickened version of this tropical variety, which I drew. More precisely, this tropical variety, tropical variety is the non-differentiable locus of H star. So H star is the supremum, is the Legendre transform of H. So I take supremum NM, where M is all the lattice points in my polytope, minus. So these would be this function will be non-differentiable whenever there are 2 candidates in this supremum which are at the same value. If we go back to this one, it connects to what I said before, that this can only be 0 if 2 of these have comparable size. So each region in the image here corresponds to this one corresponds to the monomial x cube, this to the monomial y cube, and this to the monomial c cube, and this one to the monomial xyc. And then each component here, tropical variety, corresponds to sort of, here is a region where xyc is comparable to y cube. So we actually tend to 0. We actually get this pretty strong convergence of the image, like this think set will converge to this tropical variety. And then we get doing this, we get a dual polytope, which is really a sort of the bounded component, or the boundary of these dual polytopes is the bounded component of this one. So first of all, I define my dual polytope by just all the everything such as it. So sorry, this is like in NR, the dual space to where the moment polytope lives, and then I just take all the points whose the pairing is less than h, and then this is the boundary of that. You also see here that there is some flexibility here, and you also see somehow what happens as I vary h here, because by varying h, I'm gonna. So this is a polytope where each supporting hyperplane is given by 1 point in my vertex in my moment polytope. And by varying the value of h, I can sort of move my hyperplane in and out. And I can also introduce new hyperplanes as well. So yeah, let's take a quick image here. So originally we have this picture, but then by varying, so in this word family I talked about the only places where h was not plus infinity were the vertices, and by varying the value of h here, I can move these places, but I can also sort of introduce non-trivial values on these boundary points, and that will sort of introduce more spaces. Then once we have this, there is a PDE problem which turns out to be central. So it relates to the fact that we want to produce these local special Lagrangian torus fibrations, and we want to produce them in such a way that we can actually glue them together. And this corresponds to a partial differential equation on the boundary of this polytope. So what we're looking for is a function on NR such that the gradient image of this is the gradient image of this function is exactly the moment polytope. And we want when I compute its determinant, not on the sort of entire NR, but when I restrict my psi to these open faces of my polytope, then I want to get something which is essentially constant. So let me write down a little bit about it.
We'll confuse the notation. Your del is a gradient?
Yes, that's a gradient. So, yeah.
Okay. It's a nubla.
It's enough, yeah. And I would.
It looks like the boundary
also.
of the image.
If you prefer. I notice now that I'm using the same notation for a boundary as well. So, okay, let's just sort of untangle some things here. So, first of all, this space here, it has real dimension d plus 1. The set here, I'm restricting psi to. It's the interior of the boundary. When I write the interior of the boundary of the polytope, I mean the interior of the top dimensional faces in the boundary. So the interior of the open faces.
Trouble reading over the interior. And on the right hand side, it was VNWS?
Yes, I'll get to that. before I say what the new n is, I will also say something about this, because here I'm restricting psi to something which is d-dimensional. So this is really a d by d matrix we have here. And I do this, when I compute this second derivative, I restrict to this hyperplane, which contains my phase. That gives me affine coordinates. That means I can compute this second derivative. But at least I can do this up to scaling, because this affine coordinate work. But when I do this, I get something which is invariant up to scaling. But the fact that I'm starting with a lattice polytope is actually gives sort of fixing this scaling. So there is a canonical way to compute this second derivative here, or at least a determinant of it. And similarly, there is a canonical metric. There is a canonical measure on the open phase. It's because we can restrict to the hyperplane, which contains them. That gives us, then we can look at the Lebesgue measure. But it is really only defined up to multiplication by a constant. But then the lattice structure, the boundary of my polytope fixes them.
There are easy way to see how the complex Monge-Ampère problem can be translated to this.
Real? Yes. So if you look at a torus invariant potential, then the complex Monge-Ampère measure of that is exactly the pullback of the real Monge-Ampère under the log math.
So it really depends on this answer that you made out, that the metrics that you want are like this.
Yes, yeah, exactly. So semi-flat, sometimes called, or Calabi-Yau semi-flat metrics, that they are Calabi-Yau metrics which are torus invariant. So this then has a name, well, it probably has many names, but integral surface measure. So if I draw, I can draw an, I usually just draw the same image over and over again. So here is P2. So, and we have its fuel. Then, so the surface measure, so here the surface measure is from the dual polytope, but it kind of works the same way for the normal polytope. So here, we have a surface measure here, and it's going to assign mass 3 to this phase, and mass 3 to this phase, and mass 3 to this phase. So somehow this integral surface measure, it thinks like that, that they are all equivalent. So all of this comes down to everything here comes down to most of the stuff.
Yeah. This mass is proportional to the percentage of volume that the generator stores.
Yes. Yes. So, or if we look over here, then each one of these will have mass 1. So each of these we will actually have to normalize. So each of these will have mass 3 as well, and each of them corresponds to one of these equals intersections. That's exactly how much mass is constituted.
There's no condition on the determinant in theory.
Sorry?
There's no extra condition on the determinant on the theory.
No, nothing at all. It's really only the boundary. So then, essentially by Yang Li, this is in 2019, existence of solution. This equation, let's
population.
Implies the weak metric. That's what conjecture. And so let's see how much time.
But you really want a global potential, not just on the boundary. You want functions on the
We do get a global potential.
Yeah.
We only care about its real Monge-Ampère on the actual boundary, but it needs to extend to something which is convex on the entire space. When it does that, we actually, since it satisfies this boundary condition as well, this is a Hermitian metric on the astronomical bundle. So that defines actually a Keller metric on the ambient space. It defines Keller metric on the ambient toric Fano manifold. And this is crucial because this ambient metric is restricted to Calabi-Yaus, and then compared to the real Calabi-Yau metrics, it turns out that these are asymptotically the same. They converge.
Then you apply some kind of implicit function theorem, or how does it work?
Which one?
To get the weak metric SYZ.
Yes, there is an implicit function theorem. So once you can prove that the potentials of the restricted ambient metrics converge to the potential of Calabi-Yau metrics, once you can prove C infinity convergence on large subsets, then you get the special Lagrangian torus fibrations with the perturbation argument or implicit function theorem argument. I mentioned we have all of these local special Lagrangian torus fibrations, and then we use an implicit function theorem to kind of
This is the sum,
perturb.
the perturbation, the sum.
Yes, that's fine. That's right.
It's what?
It's a page
Yes, it's pretty recent. Yeah, 2017. And then, yes, how am I doing with time?
10 more minutes.
10 more minutes. Yes. Okay. So I want to. This is kind of the important. I think I reached the important part. Like this is what it's the crucial part of this session. But I have some more things I want to mention as well. So. Another thing which is nice is that the boundary of this polytope come with this natural integral affine structure. So for each facet of my moment polytope with normal and sigma, so that on the left hand side here I have my moment polytope, then I fix one face, I get a normal and sigma. I can map, so the left hand side here lies in MR, the right hand side in NR. Then I can map and I can take the quotient of NR and sigma. That means I'm somehow identifying the vertical strips like this. That means I am mapping my and if I restrict this to the star of n sigma, so n sigma is right here, and the star is all the faces which contain n sigma, so this part right here, then it turns out that this map is injective. And then these, so what happens? So but I can do this for each face here. So here I get another map where this is my normal, and this time I'm sort of identifying these kind of strips. Then I get something which is injective on the star of this. These are coordinate charts, and where they overlap, they compatible on overlaps. So this is going to connect to some of the questions that we had here before. Let's say I do this in higher dimensions. Let's say I do this when I have not just a boundary of a polygon, but I have, say, a unit simplex like this, and I have the dual unit simplex right here. Then fixing a face here corresponds to fixing a vertex there. That means I have a coordinate chart which is a priori defined on the entire star here. And then I can do this in another point as well and get a coordinate chart on the star of that vertex. The thing here is that they're compatible on overlaps. Or let me say here, on overlaps, they're compatible on the interior of the open faces. That means when I cook up these coordinate charts here, they're going to be compatible on these open faces, but they will not be compatible on the edges. That means on each edge I need to fix a point. And if I fix a point like this, that means that the coordinate chart corresponding to this vertex is going to be sort of this part here. Excluding, I need to exclude one point on each edge like that in order to get them into a Laplace fraction. This is related to some of the images we saw before as well. Once I have this into a Laplace structure, I can compute its monodromy around these singular points. And if I do this for the unit simplex I have here, I get these 1, 1, 4. Sorry, the 0, right? Something like this, or conjugate that. This comes down to the fact that the unit simplex has 6 edges, and we're expecting to get number 24 here, a magic number. It's the Euler characteristic of a K-free surface. So, yeah, there you get this 1, 1. If you do the same thing, but instead of, so this would correspond to a hypersurface in P3. If you instead look at a hypersurface in P1 to the power of 3, that means you get the dual here would be the octahedron. I'm not sure I'll be able to draw it, but something like this. And the octahedron has 12 edges. We're going to fix one singular point on each edge. And then we get these, we're going to get the monodromy of 1, 2, 1, 0. Let's see here. I want to just say something briefly about this. So we go back to this first image here when I talked about the Calabi-Yau matrix. I said that the Calabi-Yau volume would concentrate on these deepest intersections. And the deepest intersections correspond to open faces by the boundary of the polytope. And okay, so let's go to this image right here. So the open faces corresponds to part of my Calabi-Yau, part of my hypersurfaces, and there are exactly, so if I mean the interior of an open face here, that means exactly 2 of these monomials are dominating. They have much larger modulus than the other ones. So that means that near these deep intersections in my toric Fano manifold, that is toric boundary, near these deepest intersections here, we have, well, it's the toric Fano manifold, so near the deepest intersections of the toric boundary, things looks like D+1. And then xt, near these points, is going to be dominated, the equation here is going to be dominated by two monomials, which means these hypersurfaces are essentially toric manifolds, or very close to being toric manifolds. And what they are, in fact, they are fibered, they're large annuli which are fibered over these open places. And if we have a solution to this real Monge-Ampère equation, then we can use that to pull back to a potential in the Calabi-Yau manifolds, which is almost Calabi-Yau. That's sort of how the proof goes. That's why this partial differential equation is so essential. And I think I will stop here, and then in the next talk I will maybe wrap this up a little bit, and then I'll talk about how sort of non-Archimedean geometry gives a nice, more general picture, and then I'll move back to this toric setting and talk about solvability of this real Monge-Ampère equation, because it turns out it's actually not always solvable. There are obstructions to solve it, which have some impact, but yeah, not so much.
You mean even for instance, you can write down polytope that
for which it is not solvable, yeah. This should be interpreted as an issue with the ambient space. So we have this family of Calabi-Yau, which we decided to embed into this toric Fano manifold. But there's somehow no reason to expect that this embedding is good from an SYZ perspective, whatever that means.